Good morning, everybody. So for the first seminar in presence, or I should say hybrid seminar of 2022, it is a pleasure to welcome today Alexandre Letiec, CNRS researcher at the LUT, Observatoire de Paris, and a worldwide expert on certain aspects of black holes and relativistic celestial mechanics. Alexandre is particularly well known at IAP since he defended his PhD thesis here in 2010 under the supervision of Luc Blanchet. He spent then 1 year as research associate and 2 years as MCFP Prize Fellow at the University of Maryland in the group of Alessandra Buonanno before being hired by the CNRS. Among other things, Alexandre's investigations have consisted in building a bridge between post-Newtonian approximation and perturbation theory on a relativistic background in the case of binary systems of black holes. In the former scheme, the binary separation is large and the mass is arbitrary. In the latter, the separation may be small, but the mass ratio is large. A powerful tool to compare the two approaches is the first law of black hole mechanics discovered during his thesis, of which he studied various aspects later on. More recently, his work on tidal effects of spinning black holes produced stimulating debates in the relativistic community. On the other hand, Alexandre has been regularly teaching. He made notably the MOOC Peser l'univers in 2016. He's also very active in science outreach. In 2019, he was awarded the Bronze Medal of the CNRS. Today, he will speak about another subject of interest for him, beyond those I already mentioned, namely the waveforms of binary systems of compact objects. Alexandre, you may start. So you have essentially 50 plus 10 minutes. Go ahead.
Thank you, Guillaume, for the introduction, and thank you, Verena, for the invitation. Okay, so good morning, everyone. I will indeed talk about gravitational wave from binary system of compact objects. And since I've spent a few years at IAP, I know that there is a fairly wide range of expertise of people here. And so I will not assume any previous knowledge of familiarity with gravitational wave physics or gravitational astronomy. So I will spend some fraction of this seminar introducing basically the concept of gravitational waves and how they are really complementary sources of information with respect to traditional electromagnetic waves. I will then give you a sort of summary of some of the huge amount of science that has been done over the last 5 years since the first discovery of gravitational waves. That dates back now to 2015. And I will finish by pointing out that we are now reaching a stage where some events that the current detectors are seeing are difficult to model to the point where there may be systematic effects due to our incomplete understanding of the gravitational emission from certain of those sources. So this is a challenge for theorists interested in gravitational waves. And I will describe a new class of gravitational waveform that can hopefully address those issues, namely related to intermediate mass ratio in spirals. So let's start. And of course, if there are any questions during the seminar, please feel free to stop me and ask. I don't mind being interrupted during the talk. So what is a gravitational wave? Just in one sentence, it is a tiny ripple in the curvature of space-time that propagates at the speed of light. So if you imagine that you have some background curvature in space-time with a very long length scale, then you can imagine a gravitational wave as a little ripple on top of this that propagates at the speed of light. So it will obey a wave equation. This is a D'Alembert operator acting on the gravitational wave. Potentially that wave can couple to the background curvature of your space-time. And those waves are generated by the energy momentum in space-time. So the existence of gravitational wave dates back to 1916. This is a key prediction of Einstein's theory of general relativity. Einstein predicted their existence just 1 year after he formulated his general relativity theory. And it took 100 years until they were observed physically directly on Earth for the first time. So in a space-time diagram picture with one dimension of space here and dimension of time on the vertical axis, you have two world lines of two particles, one in blue, one in red. You have a variety of light cones that tell you about the propagation of light, which are depicted here. And you can imagine a gravitational wave as this little ripple in the curvature of space-time that propagates in this direction here, tangent to the light cone at every point in space-time. So let's contrast quickly the main similarities and difference between electromagnetic and gravitational waves. So first of all, electromagnetic waves are generated by the acceleration of charges, and there are waves in the electromagnetic field that propagate in space-time, while gravitational waves are generated by the acceleration of masses, and there are waves in the curvature of space-time, there are waves of space-time itself. Typically, the wavelength of an electromagnetic wave is much smaller than the typical size of the source. The main structure, the multipolar structure far away from the source is predominantly dipolar. The coherence is low. And this is very different from gravitational waves whose wavelength is typically larger than the size of the source, which have a predominantly quadrupolar structure far away from the source and with a very high coherence. While electromagnetic waves interact very strongly with matter, gravitational waves interact very weakly with matter, which is a good thing because essentially it means that when they reach us, they are unchanged with respect to the way they look like when they were generated, but it also means that it's very hard to actually detect them. So the typical frequency of electromagnetic waves that we observe is so high that we don't track the amplitude. We basically track the average, the average value of the square of the electric field, so the power in the field, which decays as 1 over the distance squared, while the typical gravitational wave frequencies that we can see are low enough that we can actually track in time the evolution of the amplitude, and therefore we have access to a signal which decays as 1 over the luminosity distance. So if you want a very simple analogy, one might say that we can see the universe with electromagnetic waves and hear it with gravitational waves. So they're very complementary sources of information about the universe. And just like there is an electromagnetic spectrum, there is a gravitational wave spectrum that ranges from frequencies from, say, 10 to the minus 16, corresponding to a period which is of the order of the age of the universe, to high frequencies of the order of a few kilohertz, corresponding to a fraction of a millisecond. And so depending on the typical mass of the source, the gravitational waves will have a different frequency. Typically, the larger the mass of the source, the smaller the orbital frequency. And depending also on the frequency of the gravitational wave, we have different means of observing them. So from a few hertz to a few kilohertz, we use ground-based laser terrestrial interferometers like LIGO, Virgo, and CaGRA, which have been operating for a few years now. In space, there are projects to send laser interferometer like LISA, which will be sensitive between, say, 10 to the minus 4 and 10 to the minus 1 hertz also, and sensitive to more massive sources. For even lower frequencies, one can use a pulsar timing array, namely a network of pulsars which act as clocks. And at even lower frequencies, an eventual imprint of gravitational wave in the cosmic microwave background radiation. So in this seminar, we'll be mostly interested in sources which we have already seen, thanks to terrestrial interferometers, namely compact binaries in our galaxy and beyond. But hopefully we'll soon see as well isolated rotating neutron stars or eventually supernova that could take place anytime in our galaxy. So here are the promising sources of gravitational waves as a function of frequency. So as I said here, we have ground-based detectors in that high frequency range and a future space-based detectors at the lowest frequency. You have the typical gravitational wave amplitude depicted here, which is extremely small, of the order of 10 to the minus 22 or so. And so the sources that I will be mainly focused on are those we've seen, namely neutron star, black hole, but also neutron star black hole coalescences. And some of the work I will be talking about will also be relevant to model future sources for LISA, namely the coalescence of supermassive black hole binaries at the center of galaxies, as well as the spiraling of a stellar mass black hole into a supermassive black hole, so-called extreme mass ratio in spirals. So just a couple of words on the need for some theoretical work in order to be able to do gravitational wave science. One doesn't only need extremely sensitive detectors, one also needs extremely precise prediction for the shape of the gravitational wave sourced by a given physical system. So you see here a simulation of a noise realization, say in LIGO over alpha second in light blue, and hidden here is a gravitational wave signal H in red, which you can barely see, simply because its typical amplitude here is roughly a factor of 100 too small compared to the typical size of the noise. And here you see the same information in frequency space. But there is hope to actually see this buried signal if you know its shape. And then you can use the method of matched filtering to essentially filter out the noise and recover the signal. So there is a need to predict in advance precisely the gravitational waveform emitted by a given source in order to be able to look for it, and if it's there, filter the noise out and detect. So this is illustrated by the third event that was detected right after Christmas 2015 in the two LIGO detectors, in Hanford in the left and Livingston in the right. Just focus on the top panel here. You see a signal that lasts for 1 second. And the typical noise level is shown here at the level of 10 to the minus 21. And you see inside is a signal whose typical amplitude is smaller than the typical noise realization. And if you cross-correlate a template that matches the signal, which is here, and so you're going to this way to accumulate signal to noise ratio up to the point where you may claim a detection if your SNR is beyond a certain threshold that corresponds to a statistical significance that you've set in advance for yourself. And if you see the same signal in the two detectors or even more detectors, of course, it increases the degree of confidence in the fact that this is a signal of astrophysical significance. So that's all I'll say about the theoretical challenge. I'll come back to this at the last part of the talk. And I want to move to a sort of summary of some of the science that has been done over the last 5 or 6 years, thanks to the first detections. I will be fairly schematic. I will not enter much detail. My main goal is to basically convince you that there's a huge diversity of science that can be done thanks to those gravitational wave observations. So we have a network of ground-based interferometric detectors, 2 in the United States, in Hanford, LIGO Hanford, and in Livingston. There is also a European detector, the Virgo detector, which is located in Cascina, next to Pisa in Italy, which is a French-Italian collaboration historically, and more countries have joined since then. And more recently, in Japan, there is also the Kagra detector, which has a similar level of sensitivity, which has started taking data over the last observing run. And I think there are plans to build an additional LIGO detector in India. So in some other place on Earth, which is basically not in the same plane as other detectors, in such a way that one can improve the accuracy in the localization of the source. So here's the roadmap for those ground waves detectors. As you can see, there are already 3 observing runs that have taken place. The first one was quite short at the end of 2015, beginning of 2016, with the first 3 detections. It was already 5 years ago. There's been a second observing run that lasted a little bit longer, a couple of years later. And at the very end, the Virgo detector joined. The third observing one was actually split into 2 observing O3A and O3B due to well, unforeseen circumstances related to the pandemic. And in fact, this diagram is not up to date because this delay induced by the pandemic is responsible for a delay in the 4th observing run, which has not started yet, contrary to what is shown here, but will in principle start at the end of this year. And as you can see, as one moves up in time, the sensitivity of the detectors is systematically increasing in such a way that the horizon distance to detect a canonical binary neutron star in spiral keeps increasing from initially 80 megaparsec for LIGO to ultimately the target a few hundreds of megaparsec. And as you increase that horizon distance, well, by a certain factor, you increase by that factor cubed the volume of universe you have access to, and therefore the event rate. Hence, the fast increase in the number of detection observed over the last 5 years. You can see here the cumulative number of detection as a function of the effective binary neutron star time volume, which effectively grows as you have more observing time and as the network becomes more sensitive, and therefore as you have access to a larger fraction of the universe. You see that during the first observing run, there were just 3 detections, second observing run, a little bit less than 10 detection, and then about 40 detection for each of the 2 halves of the third observing run, which gives us a total of about 90 gravitational wave signals. So here's a family portrait, which strangely enough reminds, I guess, well, it looks very much like the periodic classification of elements. So this is a the analog for compact binary systems, at least temporarily, because of course this family portrait is going to increase in size a lot following the 4th observing run. So you see the first 3 detections here for O1, about 8 for O2, and an additional 80 detection during O3. And so most of those detections, I mean, all of those detections come from a binary system of compact objects, namely neutron stars and black holes whose masses may range between a few solar masses and a few tens or even now hundreds of solar masses. And what I want to do now is to show you that thanks to those gravitational wave events from compact binary systems, we can do a lot of science. A lot of science has already been done, and it ranges from astrophysics to cosmology to fundamental physics. I will not talk about all of this. It would take a very long time, but I will basically flash some representative examples. So let's start with the question of formulation and evolution of compact binary systems. So here you have the 90 gravitational wave events in the latest LIGO Virgo Cagra collaboration catalog. And so you see all those events are shown with the two bodies that merge to make a third body each time, and indicate they are classified according to the masses of the compact objects. So the main thing you see on this plot is that we start having some statistics, and basically the average ranges around a few tens of solar masses, which is a first remarkable discovery, because before that, the only stellar mass black holes we knew were through the observation of electromagnetic waves in X-ray binaries, and those masses were not so large. Some masses are especially large in the sense that we see here that there are black holes with masses of the order of 100 solar mass that merge to make what one might call an intermediate mass ratio black hole, with a black hole of the order of 200 solar masses. And certainly if you have a neutron star spiraling into a 200 solar mass black holes, that should be called an intermediate mass ratio in spiral. Binary neutron star systems have also been seen, the in spiral of two neutron stars that ends up in a merger that most likely results in a small mass black hole. Two such events have been seen. And more recently, during the last observing run, we have also seen for the first time so-called mixed binaries, one neutron star spiraling with one black hole to produce a slightly more massive black hole. Three such events. And I'll come back to this particular event here at the latest part of the talk. So given those now dozens of events, it's possible to start predict what is the isotropic gravitational wave background generated by this population of compact binary systems. So you see here, shown as a function of frequency, the contribution to this isotropic gravitational wave background to the total energy density of the universe normalized to the critical density. And you see different curves here that correspond to the corresponding sensitivities of the network. So here for O2, here for O3. So if there was some signal above that black line during O3, it would have been seen. This is the prediction for the design network that will be reached in principle in the middle of that decade, and then plan for further increase in sensitivity, which potentially will start addressing the detectability of this isotropic gravitational wave background from binary neutron star and binary black holes alone. And if you add also mixed binaries, you have an upper bound on the level of the stochastic background, which apparently is still low enough that the design sensitivity will not be enough to see it. But at some point, we will see this background. It's important to understand it and characterize it, because in a certain sense, it acts as a foreground to see another background, which would be originating from, say, more fundamental physics soon after the Big Bang, a stochastic background of gravitational wave of cosmological origin. Okay, so how about the origin and mechanisms of gamma ray bursts? Well, you've unavoidably heard about that remarkable event, GW 170817. So the 17th of August 2017, we've seen the first coalescence of a binary neutron star system, thanks to the LIGO-Virgo network. And less than 2 seconds later, the Fermi telescope saw a short gamma ray burst. A few hours later, a network of ground-based optical telescopes have identified the electromagnetic counterpart to this multi-messenger event. And so it was this point that appeared in this galaxy NGC 4993, which is located inside the common region of observation, of a prediction of the location of the source between the LIGO-Virgo network and the Fermi detector. So this was the first confirmation, indeed, that the progenitors of a short gamma ray burst are indeed, as was long thought, the coalescence of two neutron stars. And it has led to the first multi-messenger astronomy event, in the sense that following this gravitational wave detection and this gamma ray observation, there's been observation of the electromagnetic counterpart, the afterglow, over the coming over the following days and even weeks and months, all across the electromagnetic spectrum, from X-ray to radio. And so that was very important for many reasons. One of them, as far as gravitational waves are concerned, is that given the very short delay in arrival between the electromagnetic wave and the gravitational wave, one can put a very strong bound on the difference between the velocity of electromagnetic waves and gravitational waves. And one can say that gravitational waves propagate at the speed of light, the vacuum speed of light, up to a fraction of the order of 10 to the minus 15. So an extremely strong bound. As far as fundamental physics is concerned, we can now for the first time do a test of general relativity in the generally strong field regime, where the gravitational field is dynamical and black holes are involved, for instance. So here is a so-called consistency test for the final mass and spin of black holes in a binary black hole coalescence. So the idea on this diagram is that you detect a binary black hole system. In the early part of the gravitational waveform, you may infer what are the masses of the two bodies. And from the late part, from the so-called gravitational wave ring down, you may infer what is the final mass and spin of the equilibrium black hole that resulted from that coalescence. And the theory tells you that there should be a relation between the two initial masses and the final mass and spin. And so you can check whether this is consistent by looking at basically the difference between what is predicted from the early part and the late part. This is the delta MF, the difference in final mass over the mean value, and same with the final spin. And as you can see, for half a dozen such binary black hole systems, you have measurements which are consistent with zero, which is in a sense a null test or a consistency test that the gravitational waveforms from those systems is consistent with the prediction of general relativity. You see that the error is of the order of a few 10, 20%. So these are not yet very accurate tests, but of course, as you have more even, you can accumulate data and make that test by combining the data, make that test more stringent. Another way of testing gravity theory is to look more finely into the structure of the early part of the in spiral, where the post-Newtonian approximation that Guillaume introduced provides a very good approximation for the motion, the orbital motion and gravitational wave emission from the system. And so the typical phase as a function of the frequency of the gravitational wave will be written as a series expansion in the frequency with some coefficients, little phi here, which depend on the physical characteristics of the binary, typically the masses, individual spins, and so on. And so given the knowledge of those two masses, which you can infer, for instance, from the leading term, you have a prediction for the next order terms. And so you can check whether or not, by measuring separately those terms, the values are consistent with the prediction from GR. And you see that for all those terms from so-called -1 post-Newtonian order to 3.5 post-Newtonian order, for those 5 signals, all the coefficients are consistent with the GR values. So you can condense this information onto that plot, where as a function of the post-Newtonian order, you have, again, half a dozen gravitational wave events eventually combined in this gray square here. And you see the constraints on possible deviation from the GR values. So the most stringent constraint is on the so-called -1 post-Newtonian order coefficient at the level of almost 0.1%. And this, in fact, corresponds to the potential emission of so-called dipolar radiation. Remember, I said that the leading structure of the gravitational wave emission is quadrupolar in general relativity. Well, if you have eventually a scalar field and not just a metric field, then there could be, in principle, dipolar radiation. And this puts a very strong constraint on the existence of such dipolar radiation. Yes? Each point is an upper bound. And when you combine all of them, you get the most stringent upper bound, which is the symbol here. So each color and form of the symbol is for a different event, but then you can combine them to make the bound more stringent. Another interesting effect is that the so-called 1.5 post-Newtonian order, which was studied long ago by Luc Blanchet here and Thibaut Damour, which has to do with the so-called gravitational wave tail effect. Namely, the fact that when a gravitational wave is emitted by a system, it will not propagate as if it was in flat spacetime, in Minkowski spacetime. In fact, it will backscatter off the background curvature generated by the total mass of the source. And that appears as a very specific signal that you can test and put a constraint here, which is already at the level of 10%. So this is a really genuinely strong field effect in curved spacetime, which is now being tested thanks to those observations. Another interesting test has to do with the last part of the signal, the so-called ring down. So after the two black holes have merged, there is a final black hole which is still excited, deformed. It's going to still radiate some gravitational wave to reach an equilibrium state. And that radiation typically takes the form of a sum of quasi-normal modes, namely damped sinusoids, which are characterized by typical damping time tau and oscillation frequency f. And the sum of the modes, L is the multipolar order, M the azimuthal number, and the harmonic. So the leading mode, the mode which is most easy to see, is the 2-2-0, so quadrupolar and fundamental. And so you can test that given the mass and spin of the black hole remnant, the values of the oscillation and damping time that you measure is consistent with the prediction of GR. And that's a delta F and delta tau, and you see that they are compatible with 0, with, again, an error bar, which is still fairly large because we don't have much signal and not much SNR, signal to noise ratio, in the very last part. But as the sensitivity of the network increases, there will be more SNR in that part, and even more with future detectors, and therefore more accurate tests. So time is flying, so I'm gonna accelerate a little bit. Well, I just want to mention that thanks to this very stringent bound on the velocity of gravitational waves, so as I said, the value cannot deviate from the vacuum speed of light velocity by more than 1 part in 10 to the 15. So that means that any theory of gravity, which is not GR, which predicts a velocity for gravitational wave which is significantly different from the speed of light, is out. So you exclude this way all of those theories which are not viable, just with one observation of a binary neutron star system and an electromagnetic counterpart. Yes.
There was a question in the chat whether
yes.
the contours that you showed in the previous plot
yes.
are 2 sigma or please repeat my question.
So the question was, did he say whether the contours are 2 sigma equivalent or what? So I didn't say whether it was 2 sigma or not. Actually, I don't remember if it's 1 sigma or 2 sigma. Well, the reference is there, Francois, if you want to check. I don't remember by heart whether it's 1 sigma or 2 sigma. Sorry. Okay, I'll skip the test of the knowledge we can infer for the internal structure of neutron stars, because I want to keep time to discuss other things. I will mention, I guess, something which is extremely important in cosmology, which is an independent measure of Hubble's constant, and more importantly, an unbiased measure of Hubble constant, or at least potentially not as biased as other measurements. So over the last 5-10 years, there's been this increasing tension between two measurements of the Hubble constant, between, on the one hand, the Planck data, with the CMB, and on the other hand, the observation of light curves from TAP 1A supernovae. Now the two measurements are clearly not so compatible given the error bars. There's a significant tension. So it's extremely important to have an independent way to measure the Hubble constant, and an event like the coalescence of two neutron stars and the observation of an electromagnetic counterpart provides a perfect way to do such a measurement, because on the one hand, of course, the electromagnetic counterpart gives you access to the redshift of the event. And on the other hand, the gravitational wave gives you a direct access to the luminosity distance in a non-biased way, because the amplitude of the gravitational wave is inversely proportional to the luminosity distance. So if you only take one event like GW 170817, this is the black measurement here. So you see there is a significant error. But the mean value is basically more or less in between the value from Planck and Type 1a supernovae. But if in addition you collect information from the luminosity distance of many events of binary black hole systems, but without electromagnetic counterparts, but you correlate those observations with galaxy catalogs, basically you notice that, okay, that particular binary black hole event, which is at that distance, is located in that region of the sky, and in that region of the sky, there are those galaxies which have those redshifts. Then in a statistical way, you can basically try to infer the redshift associated with those events. It's not as good as if you have a direct measurement, but it's still better than nothing. And it allows you to have this blue curve, which, as you can see, is a more precise measurement, but still not competitive compared to other methods. But you now see that the measurement is of the order of 68 kilometers per second per megaparsec, and the accuracy is well, 10% or so, and will improve as the size of the catalog increases in the future. One can also get some estimation of the evolution of the Hubble parameter with redshift, but I'll skip this. I'll skip cosmic strings. I'll briefly mention that the future of gravitational wave will also take place in space, thanks to the LISA mission, which is a planned mission, which is currently being studied. It's been accepted by the European Space Agency in 2017 for the third large mission slot. Sorry? Approved, yes. Thank you. And launch plan for 2034. So LISA will observe sources which are completely different from ground-based sources, such as the coalescence of a binary system of supermassive black holes with masses ranging from 10 to the 5 solar masses to 10 to the 7 solar masses, which will be observed for a very long time, from hours to eventually several years, and with very large signal-to-noise ratios. It will also see tens of thousands of galactic binaries, typically white dwarf binaries in our galaxy, including some so-called verification binaries, because we know where they are, we know their position, and so we can check the monochromatic gravitational wave emission from such sources. There are so many of them that actually they will constitute a galactic background. And most interestingly, at least for me, the inspiral of stellar mass compact objects, so neutron star or stellar mass black holes, into supermassive black holes at the center of galaxies, the so-called extreme mass ratio inspirals. Here you can see a few harmonics, because the orbital motion is extremely complicated, so the gravitational emission will be extremely rich and full of information. Those curves here correspond to some stellar mass black hole binaries, which will be seen as well by LISA in such a way that it will be possible to predict beforehand with a lot of accuracy the location of such sources in the sky and the time they will coalesce in the LIGO-Virgo-Cagra band. So there will be multi-band gravitational wave astronomy, which is also extremely promising. I'll skip test of the black hole no-hair theorem, but if you have questions, I'll be happy to come back to this. It's, I think, fascinating. And for the last 10, 15 minutes or so, I want to, I guess, emphasize some of my current research, which is motivated by the fact that LIGO, Virgo, and Cagra are now starting to see sources which are difficult to model. So if you go back to this event, where basically a neutron star with a mass a little bit more than 1 solar mass has spiraled and coalesced with a 25 or 30 solar mass black hole or so, we now have an event which may be called an intermediate mass ratio in spiral, because the mass ratio is of the order of a few tenths. And these are quotes from the latest LIGO, Virgo, Cagra collaboration catalog, the O3 catalog, where they write explicitly that such sources are extremely challenging for waveform modeling, and thus there may be systematic uncertainties in results for these candidates. So in other words, the quality of the science we can infer from such detections is now limited by the quality of the theoretical prediction for the waveform. And it's extremely important in particular to account for higher order multipole moments in the gravitational wave emission, because not accounting for them will impact the inference of the parameters, such as the mass ratio, the inclination, or the distance. And therefore, all of the science I described earlier, which depends upon a proper estimation of the physical parameters of the source. So this is to motivate the need for a new class of gravitational wave templates, which can successfully describe, model the wave emission from such intermediate mass ratio in spirals. And on the market of methods, we basically have 3 or 4 main methods, which I'm showing here on this diagram with the mass ratio on the left axis, which ranges from equal mass here on the left to extreme mass ratios on the right. And on the y-axis, I'm showing the typical separation between the two bodies divided by the total mass. So this is the inverse of the compactness parameter of the source, from two bodies that merge down here to a large separation up here. So whenever the separation is large enough, the orbital velocity, because of the virial theorem, will be small compared to the speed of light. The gravitational field will be weak, and one can solve the Einstein equation perturbatively around the Newtonian solution, thanks to the post-Newtonian approximation, which is the specialty of people like Luc Blanchet and Guillaume Fay at IAP, and will provide accurate waveform for any mass ratio during the inspiring phase. But will break down at some point as the separation becomes too small and the orbital velocity too close to the speed of light. There is a complementary approximation scheme based on black hole perturbation theory whenever the mass ratio is large enough. So the idea now is that you have, say, a supermassive black hole and a stellar mass compact object orbiting around it. The small parameter is the mass ratio. In first approximation, your space-time is just that of the big body. And then you can add successively perturbations due to the small body, which will radiate gravitational waves, and those waves will actually back react on the motion, giving rise to a so-called gravitational self-force that will make the body deviate from what would otherwise be a geodesic. And in principle, this scheme will work for any separation, including strong fields, when the bodies are very close to each other, close to merger. But one would expect that it would only work if the mass ratio is large enough. And finally, when you have comparable mass black holes close to merger, well, they will, both approximation schemes should break down, and one needs to solve the Einstein equation numerically using supercomputers. And this is the field of numerical relativity. So in principle, numerical relativity provides you the exact result over the entire parameter space, but in practice, it's limited by computational time, because whenever the orbital separation is too large or the mass ratio too extreme, there is such a large separation of scale that you would need to run the simulation for a prohibitively long time. hence the limited space accessible to numerical relativity. So at the end of the 1990s, Alessandra Buonanno and Thibaut Damour introduced a framework called the effective one-body framework, which aims at extending the domain of validity of post-Newtonian theory into the strong field regime. The basic idea is to map the actual real dynamics of the two-body system onto the dynamics of an effective particle whose mass is the reduced mass of the system into an effective geometry of a deformed Schwarzschild geometry associated with a total mass, just like one would solve the Newtonian two-body problem exactly using such an effective description. One is effectively, why is it not charging my computer? That's strange. Well, I hope it's not gonna turn off because sorry about this interruption, but I'm just worried that it's gonna stop right in the middle. It's good to say it's charging. It says it's charging, but it also says there's almost no battery, so it's kind of weird. But it should be fine. Okay. So this is one technique to eventually try to extend the domain of post-Newtonian theory. Actually,
on t'entend moins bien.
On post-Newtonian results. There is an alternative idea which I've been pushing for the last 10 years, which is to try to extend the domain of validity of perturbation theory all the way to more comparable masses, or at least intermediate mass ratios. And the idea is very simple. In perturbation theory, from the start, you're essentially treating the two bodies on an unequal footing because one is perturbing the other. But you know that in the real solution to that two-body problem, there should be a discrete symmetry by exchange of the two bodies, which is manifest in post-Newtonian calculations. There's a problem with my microphone. There. Thank you. Sorry about that. So I was saying that, what's the last thing that was heard? Ah, okay.
That's fine. That's fine. Keep going.
Okay. So the key idea is that you want to restore a posteriori in the prediction from perturbation theory the discrete symmetry by exchange of the two bodies that should be there from the start. So in practice, it essentially means re-expressing the asymmetric mass ratio in terms of the so-called symmetric mass ratio, which is the reduced mass divided by the total mass. You can do this in a mathematically consistent way to the order at which you control your series expansion in the mass ratio. And this is a way to a posteriori restore some information that you know you've broken as you started your calculation. And so there are now many examples of comparisons of the predictions of perturbation theory and the gravitational self-force framework to the exact result from numerical relativity that show that if you do this, you get an extremely good agreement in such a way that you can extend perturbation theory all the way to the comparable mass regime, both for the orbital dynamics, the relativistic orbital dynamics of the binary system, and the gravitational wave emission in many different situations, like including the head-on collision of two unequal mass black holes or the in-spiral. So let me show you here this diagram, which is a sort of scientific precise version of the sketch I was showing earlier with the mass ratio here on the x-axis, the symmetric mass ratio equivalently. And on the y-axis, the separation from small separation to large separation, or equivalently the orbital frequency from a large orbital frequency to small orbital frequency. So this is the domain where you have numerical relativity prediction. The post-Newton approximation works well for large enough separations, but at some point becomes inaccurate when the separation becomes too small. And you see that the small mass ratio approximation, perturbation theory, the gravitational self-force framework, if you use the symmetric mass ratio, extends all the way to the relativistic regime and overlaps with numerical relativity. So 10 years ago, Adam Parn and some collaborators have started a long and challenging research program that has to do with doing perturbation theory of black holes to second order, the second order gravitational self-force framework. And there have been many results in between, including some key results, which I unfortunately don't have time to discuss. So the main point I want to emphasize is that this framework is now able to predict the energy of a binary system and the flux of energy and the gravitational waveform accurate to second order in the mass ratio, or the symmetric mass ratio. And one can then ask the question, how do those waveforms compare to the exact waveform from numerical relativity? So I'll show you the key takeaway message, which is on this plot. You can see the leading mode, the so-called tutu mode, the quadrupolar mode of the gravitational wave strain as a function of time, both using numerical relativity. This is the black curve, and the prediction from second order self-force theory using the symmetric mass ratio I introduced earlier. Here, not for an extreme mass ratio in spiral, but for an intermediate mass ratio or even comparable mass system where the mass ratio is 10-to-1. So you can see that the analytic prediction is extremely good during the entire in spiral, all the way almost to merger. In the bottom part here, in the bottom panel, you see the very last orbits. Here, this is basically where the two black holes are merging, and then you have the ring down I mentioned earlier in the talk. So you see that they remain in phase extremely, well, in a very satisfactory manner, all the way to the very last orbits. At some point, this scheme will break down because it's built on a 2-time scale approximation, and one needs to transition to another description in terms of a plunge, transition to plunge, which is ongoing work. But so we are very, well, very optimistic that that doing so will be able to cover the entire in spiral to merger to ring down using perturbation theory, not only for extreme mass ratio in spirals, but also for comparable mass systems. So this is mass ratio 10-to-1. These are equal mass black holes. You see that the agreement again is extremely good. The blue curve you see here is when you only do first order.
Yeah. There is a question in the chat.
Okay.
So what is the gray or blue?
Blue equal gray. Yeah, blue equal gray. What is the blue curve? Okay. What is the gray curve? Yeah. So that's what I was about to say. This is when you only do the leading order approximation. So the so-called adiabatic approximation relying on first order perturbation theory or first order gravitational self-force theory. If you go to the next order, second order, you have the yellow curve. So the blue curve clearly is not good enough. You're not accurate enough. So here I'm showing the amplitude, the mode amplitude of the waveform as a function of time for mass ratio 10-to-1 for several multiples, so 2, 2, 3, 3, 4, 4, and 5, 5. So remember that it's very important for such systems when the mass ratio becomes larger and larger to include higher order multiples. So you can see that those higher order multiples are extremely well modeled all the way to almost the plunge, with basically differences which are compatible with the numerical relativity error. I'll skip this. And finally, the most important information is the phase, because when you do match filtering, you want your template to be in phase with the physical signal which is in your data. And so here you see the accumulated dephasing in the tutu mode. between the model from perturbation theory, self-force theory, and numerical relativity for a variety of mass ratios. So the blue or gray curve is the adiabatic approximation, the leading order scheme based on first order perturbation theory, which clearly is not good enough because you get dephasing of order 1 or more way before the merger in all cases. But as you include already, as soon as you include the next order effect from second order perturbation theory and second order gravitational self-force, you get the yellow curves, which remain essentially compatible with numerical relativity all the way to the very last orbits with a dephasing less than 1 radiant for all mass ratios here. Since I'm out of time, I'll leave you with a summary. So I'm not going to summarize the science. I hope I convince you that it's very broad, it's very interesting, it's very rich. And I'll leave you with, let's say, some conclusions regarding the state of the art. We're now starting to see signals which are difficult to model and may result in systematic effects. So it's important to have new classes of waveforms which can model those sources. And it seems like second order gravitational self-force theory will be very good for this, and it will be able to model not only extreme mass ratio in spirals for LISA, but also intermediate mass ratio in spirals, both on the ground and in space, and even possibly comparable mass systems. And thank you for your attention.
Thank you very much, Alexandre. So it's time for question, and for simplicity reason, we will start with the audience here at IAP, and then we will. Yeah, but I mean, I see that there are already questions on Zoom, but let us first start with the audience. There are only a few people, so I guess it is reasonable to do that. So if any question here, yes, so Irina.
Okay, thank you for this talk. I had a sort of more general question. Like you discussed, one of the goals of future experiments will be to detect deviations from GR. So how do you see it in the context of these uncertainties that we will always have some uncertainties in the waveforms? Suppose we detect some deviations from GR. How certain can we be that this is a deviation from GR and not a waveform systematic?
Well, I have a fairly strong and I think not well shared view on this. I tend to be fairly skeptical that it will be easy or even possible in the near future to claim with the level of certainty required for such a huge claim that we've detected a deviation from GR, precisely because whenever we'll see a deviation from the prediction, I think the first thing we'll need to check is that there's no astrophysical cause for this deviation. May it be some accretion disk for LISA sources, maybe a third body going around. And I'm not a specialist in that field. I know there's a lot of work in that field. I'm just going to wait and see until we can exclude all of those sources to explain a deviation from the prediction from GR, until we can really make sure we've seen such a deviation. I think it's going to be more challenging than what we currently hear, but this is just my personal point of view.
Thank you. There was, I think, another question by Jacopo.
Hi, very nice talk. So I have a couple of questions, but I will even more. Okay. So one of these last points you discussed, the kinds of event for which we don't have currently the state of the art is that there are no templates. That is it possible, naively speaking, that there were signals hidden in the data that we could have missed already because of that?
Well, is it possible? I guess in principle it is possible. is it likely? To be completely honest, I don't think I can really answer your question because I'm not familiar enough with the search method. There are several search methods. I mean, I mentioned the match filtering, but there's also a method based on look for excess of power in a time frequency space. And so I imagine the people who are really doing the data analysis are quite confident in the fact that they can detect any signal that's there given a certain SNR and given accurate enough waveforms. Now, to really answer your question, one would need to be able to quantify, say, whether current waveforms would be unable to match an actual signal that is in the data with a large enough SNR. I'm not sure, but I would think probably that's not going to happen. I think what would happen is that your waveform, when you're searching over parameters, so somehow what will happen is that for some set of parameters, you'll have a waveform that'll match a signal. The issue will be in the estimation of the parameter. It's like your waveform maybe not accurate enough to correctly predict measure the values of the parameters. So there will be a bias, but still it will have enough flexibility in a sense because the structure is simple enough that you can detect the signal. So my guess, but I think you should ask the question to someone who's really a specialist of data analysis of the signal. My guess is, no, they are not missed, but eventually there will be some bias in the estimation of the physical parameters.
Very last one. So when you show the sensitivity curve for the stochastic background, so it looks like that in the next run, we will be close, but not enough to see so this blue band. So what is the last curve that you plotted like this?
This one?
This dash dot is the most, in the sensitivity.
This one?
Yeah.
So this one is not for the next run. So this was the last run. This is not even for the next run, 04. This will be more 05 if 05 reaches design sensitivity for the so-called advanced detectors. And this are plans for even later in the future, where you keep using your detectors, even though you're building new generations of detectors like the Einstein telescope. And so they're even more challenging. So this is probably not before the end of that decade, that curve.
Okay, thanks.
Thank you. And I think now we can go to Zoom. I think there was a hand raised by Sylvia, if I remember correctly.
Yes. Can you hear me?
From Sylvia. Yes, so Sylvia, you can ask your question.
Yes. Thank you very much for this very nice talk. I was wondering whether you can comment on the rate of events with the electromagnetic counterparts. You mentioned briefly, the constraints on H0. And I was wondering whether you would have expected more events from 03, to observe another, at least another event with an electromagnetic counterparts. Can you comment on this?
Hi, Sylvia. I can comment that I would have expected, I guess, more binary neutral star systems with eventual electronic counterpart, but that expectation was based on just one event. So it's really hard to make accurate predictions with just that poor statistics. It appears that maybe we were a little bit lucky. But what seems clear to me is that as we're moving to the next runs, we are significantly increasing the event rate. Like I mentioned, if you double, just doubling the sensitivity means basically increasing the event rate by a factor of 2 to the 3, so almost 10. So even if the event rate is intrinsically not so high, it seems, well, I'm not building the experiments. I don't know how difficult it is to gain a factor of 2, but it seems to me, given at least the plan and given what has happened over the last 5 years, that there are chances that will, well, chances, I can't quantify those chances, but it doesn't seem crazy to me that by the end of this decade, for instance, we'll have more such events. Now, will we have dozens of such events? At that point, that seems unlikely, but I haven't read any paper that tries to quantify this precisely. Maybe they exist, but I'm not aware of them.
Okay, thanks. Yeah, I'm just thinking about the promise that, you know, gravitational waves will measure H0, you know, very well, and we need tens of events to, you know, bring down the uncertainty to the level of Planck or Schuss. And I think, you know, when the first one came out, the promise was in the next 5 years, you know, we will have a measurement of H0, which with a small error bar already. And, you know, we're in 2022 and this hasn't happened yet. So I was just wondering.
I would be surprised that that was claimed in the paper by the collaboration, because the collaboration tends to be quite conservative and not to make strong claims like this. But that one doesn't necessarily need such events with electromagnetic counterparts. As I showed, one can actually use a correlation between the luminosity distance of the event and the localization in the sky together with the galaxy catalog. And as your network increases in sensitivity, but also in the accuracy in the localization of the event in the sky, which will be the case with LIGO India, you can decrease the number of galaxies in the catalog, and therefore, I think, improve the quality of that correlation. And just with binary black hole events, improve the accuracy of the measurement of H0. Maybe not to the level of accuracy that you would want, but certainly it will improve.
Okay, thanks.
Okay, thank you. I think you can lower your hand if it's not done. And there was a question by Mark, if I saw correctly, but I don't see him anymore. But Mark, if you have a question, you can ask it.
I was going to say what Alexandre pointed out about the statistical approach, and I was just wondering, well, to what extent that would ever be competitive with the multi-messenger approach as far as measuring H0. I don't know if there's an answer to this yet, or if higher statistics can actually be competitive with the multi-messenger approach.
Hi, Mark. I don't know. I don't have the answer to that question. Yeah, I don't know.
Thank you.
Thank you. So there is now a question by Rafael. So you can ask your question.
Hello, nice to see some of you again. If I can answer the question that Marc Lille asked. So indeed, if you take into account the afterglow counterpart as a way of measuring the inclination angle to these BNS systems, and thus to have a better estimate for the luminosity distance and entail a better measurement of H0. It's true that afterglows help. However, if you do the statistics, you realize that the afterglow counterparts will be very, very rarely detected because they're so dim and because they depend very steeply on the angle. So on the long run, the rareness of these counterparts will not allow the multi-messenger approach to measure H0 better than if you just take into account the redshift of the host galaxy and the distance from the GW data. I can link to a paper if you like on that topic.
Thank you for what was actually not a question, but an answer. So if you have other questions, comments, it's time. If I don't see any, I think we can thank our speaker again. Thank you, Alexandre.
Thank you.
And see you next time, everybody. Goodbye. Voilà, ça nous a fait plaisir.
Ça me fait plaisir de venir aussi.
Très bon talk, Alex.
Merci. Ça va mieux le pied?
Ouais, ça va mieux, ouais.